the depths of Montana's Badlands, where ancient rock layers tell stories spanning millions of years, paleontologist Sarah Chen made a discovery that would challenge everything scientists thought they knew about dinosaur evolution. The autumn wind whipped across the excavation site as her brush carefully cleared away millions of years of sediment, revealing something that shouldn't exist: a skull that defied all conventional understanding of prehistoric life. The fossilized remains emerged from the Jurassic rock layers, dated precisely to 150 million years ago, yet its features suggested capabilities that wouldn't evolve for another 70 million years. The specimen's brain case showed unprecedented complexity, with neural pathways and sensory structures that resembled those of much later predators. Chen's hands trembled as she documented each impossible detail: the enlarged olfactory bulb suggesting advanced smell processing, the expanded optical lobes indicating superior vision, and most strikingly, the presence of specialized structures previously thought to have evolved only during the late Cretaceous period. How could a creature from the Jurassic period possess neurological features that wouldn't become common until tens of millions of years later? The excavation team worked meticulously through the remaining daylight hours, their excitement building with each new piece of evidence. The fossilized skull, nearly complete and exquisitely preserved, revealed a predator unlike anything previously discovered in Jurassic rock formations. Its teeth, while similar in basic structure to those of other theropod dinosaurs, showed specializations that suggested hunting capabilities far beyond what should have been possible for its time. The bone density and attachment points for muscles indicated a level of athletic prowess that seemed evolutionarily premature. As the sun set over the Montana landscape, casting long shadows across the excavation site, Chen and her team faced a profound question. What were they looking at? The fossil's location in the rock strata was undeniable. It was Jurassic, specifically from the Kimmeridgian age, approximately 157 to 152 million years ago. Yet its features suggested a level of evolutionary advancement that should have been impossible for that time period. The team had uncovered what appeared to be a temporal anomaly preserved in stone. What forces could have driven such advanced adaptations so early in evolutionary history? How had this creature developed characteristics that paleontologists had always assumed required millions more years of evolutionary refinement? And perhaps most intriguingly, why had no similar specimens been found before? These questions would soon spark a scientific debate that would reshape our understanding of dinosaur evolution and challenge long-held assumptions about the pace and pattern of evolutionary change. The implications of the discovery began to ripple through the scientific community, even before the specimen was fully excavated. If a predator with such advanced features existed during the Jurassic period, what other assumptions about evolutionary timing might be incorrect? Could there have been other equally advanced creatures whose fossils simply haven't been discovered yet? The find suggested that the evolutionary history of predatory dinosaurs might be far more complex than previously thought, with sophisticated hunting adaptations appearing much earlier than anyone had imagined possible. As night fell over the excavation site, the team carefully covered their extraordinary find, knowing that the next day would bring more revelations and, undoubtedly, more questions. The mystery of this advanced Jurassic predator was just beginning to unfold, and its implications would force paleontologists worldwide to reconsider fundamental aspects of evolutionary theory. What other secrets lay hidden in the ancient rock layers of the Earth, waiting to challenge our understanding of prehistoric life? The following weeks transformed the quiet Montana research facility into a hub of intense scientific activity. Dozens of specialists converged on the laboratory, bringing their expertise and sophisticated analytical equipment to bear on the enigmatic specimen. Initial CT scans revealed internal structures that left even veteran paleontologists speechless. The creature's semicircular canals, crucial for balance and spatial orientation, showed a degree of development previously thought impossible for the Jurassic period. These delicate structures, preserved in exceptional detail, suggested a level of agility and coordination more commonly associated with advanced Cretaceous predators or even modern birds. Detailed analysis of the skull's proportions and features painted a picture of a predator that shouldn't have existed. The brain cavity was 25% larger than any known Jurassic theropod, with expanded regions dedicated to sensory processing and motor control. The orbital sockets, positioned for optimal binocular vision, indicated hunting capabilities far beyond those of its contemporaries. Every new measurement and observation seemed to push the boundaries of what scientists thought possible for a Jurassic predator. Multiple dating methods confirmed the impossible age of the specimen. Radiometric dating of the surrounding rock matrix, analysis of nearby index fossils, and examination of the geological context all pointed to the same conclusion. This creature had indeed lived during the late Jurassic period, approximately 154 million years ago. The sedimentary layers told a clear story, with no sign of disturbance or mixing that might have explained the presence of a more recent fossil in older rocks. The creature's teeth revealed another layer of evolutionary sophistication. Unlike the relatively simple serrations found in other Jurassic predators, these teeth showed complex patterns of wear and specialized serrations that suggested highly efficient killing capabilities. Microscopic analysis revealed blood grooves and specialized enamel structures that would have made them exceptionally effective at both piercing and cutting, adaptations previously thought to have evolved much later. The question that kept arising was how such advanced features could have evolved so early. Traditional evolutionary models suggested that complex adaptations required long periods of gradual development, yet here was evidence of sophisticated hunting adaptations appearing tens of millions of years too early. What selective pressures could have driven such rapid evolution? What environmental conditions in the Jurassic period might have favored the development of these advanced features? As researchers compiled their findings, they began to realize that this discovery wouldn't just add another species to the fossil record, it would fundamentally challenge our understanding of evolutionary timing and development. The presence of such advanced features in a Jurassic predator suggested that the capacity for rapid evolutionary innovation might be far greater than previously thought. Could other prehistoric creatures have developed similarly advanced adaptations that haven't been preserved in the fossil record? The implications extended beyond paleontology into our broader understanding of evolutionary processes. If complex features could evolve so much earlier than previously thought possible, what did that mean for our models of evolutionary change? How many other assumptions about the timing and sequence of evolutionary innovations might need to be reconsidered? The discovery forced scientists to confront the possibility that evolution might be capable of producing sophisticated adaptations much more quickly than traditionally believed. What other evolutionary impossibilities might be waiting to be discovered in the rock layers of Earth's past? How many other creatures might have developed advanced features millions of years before we thought possible? These questions began to reshape the landscape of paleontological research, suggesting that the history of life on Earth might be far more complex and dynamic than anyone had imagined. The scientific community's response to the Montana discovery quickly evolved into one of the most heated debates in modern paleontology. Established researchers found themselves divided into opposing camps, each struggling to reconcile the new evidence with existing evolutionary theories. The specimen's features seemed to violate fundamental assumptions about the pace and pattern of evolutionary change, leading to intense disagreement about its implications for our understanding of dinosaur evolution. At the prestigious annual meeting of the Society of Vertebrate Paleontology, heated discussions erupted as competing interpretations of the evidence were presented. Dr. Marcus Thompson from Oxford University argued forcefully that the specimen must represent an isolated case of convergent evolution, where similar features evolved independently in different time periods. His presentation highlighted other examples of convergent evolution in the fossil record, suggesting that the advanced features of the Montana specimen might have evolved separately from their later Cretaceous counterparts. However, Dr. Yuki Tanaka from the University of Tokyo presented a more radical interpretation. Her analysis suggested that the specimen might represent an entirely unknown lineage of advanced predatory dinosaurs that evolved sophisticated hunting adaptations far earlier than previously thought possible. She proposed that this lineage might have existed alongside more primitive forms, perhaps eventually going extinct and leaving no direct descendants. This lost lineage hypothesis challenged conventional views about the progressive nature of evolution. Further controversy emerged when detailed biomechanical studies revealed that the creature's hunting capabilities would have far exceeded those of any known Jurassic predator. Computer simulations based on the fossil evidence suggested it could achieve speeds of up to 45 miles per hour in short bursts, a level of performance previously associated only with much later theropods. The question of how such advanced locomotor abilities could have evolved so early became a central point of contention. The debate intensified when researchers discovered evidence of specialized blood vessels and potential thermal regulation structures in the fossil. These features suggested a level of physiological sophistication that many paleontologists had assumed evolved only in the late Cretaceous period. Could this creature have possessed an advanced metabolism tens of millions of years before such adaptations were thought possible? What implications would this have for our understanding of dinosaur physiology and evolution? Critics argued that the specimen must represent some form of preservation artifact or taphonomic distortion, changes that occurred during the fossilization process. They pointed to examples of other fossils where preservation conditions had created misleading appearances. However, multiple independent analyses confirmed the authenticity of the features, leaving skeptics struggling to explain the mounting evidence. The controversy spread beyond academic circles, as implications of the discovery began to challenge popular understanding of dinosaur evolution. If such advanced predators existed in the Jurassic period, how many other assumptions about prehistoric life might need to be reconsidered? What other evolutionary innovations might have appeared far earlier than previously thought? The debate forced paleontologists to confront the possibility that their understanding of evolutionary timing might need substantial revision. As researchers grappled with these questions, new methodologies and analytical techniques were developed to study the specimen. Advanced imaging technologies revealed ever more detailed information about its anatomy and capabilities, while sophisticated statistical analyses attempted to quantify the probability of such advanced features evolving so early. Each new study seemed to raise as many questions as it answered, fueling continued debate about the implications of this extraordinary discovery. What other evolutionary surprises might be waiting to be discovered in the fossil record? How many other advanced creatures might have existed millions of years before current models suggest they should have evolved? These questions began to transform paleontology from a field focused on documenting the known progression of evolution into one increasingly open to the possibility of unexpected and dramatic evolutionary innovations throughout Earth's history. The painstaking process of reconstructing this ancient predator revealed a creature that would have dominated its Jurassic ecosystem in ways previously thought impossible. As researchers assembled the complete skeletal structure, they uncovered a perfectly balanced killing machine that combined the raw power of early theropods with the sophisticated hunting adaptations of much later predators. The specimen, now officially named Temporalis paradoxus, meaning paradoxical creature of time, measured approximately 35 feet from snout to tail, with a skull nearly 6 feet in length. Advanced computer modeling techniques revealed that Temporalis possessed a bite force exceeding 4,000 pounds per square inch, surpassing that of any known Jurassic predator. The creature's jaw mechanics showed evidence of specialized adaptations that would have allowed it to deliver precision strikes while maintaining incredible bite strength. Microscopic analysis of tooth-wear patterns suggested hunting behaviors previously thought to have evolved only in the late Cretaceous period, including specialized techniques for taking down large prey. The specimen's forelimbs presented another evolutionary puzzle. Though relatively short compared to its overall body size, they showed evidence of highly developed muscle attachments and sophisticated joint structures. These features suggested capabilities far beyond those of other Jurassic theropods, including the ability to manipulate prey with unprecedented dexterity. The question of how such advanced limb structure could have evolved so early became a central focus of research efforts. Analysis of the creature's vertebral column revealed another startling discovery. The cervical vertebrae showed specialized air sacs and pneumatic features previously thought to have evolved only in the ancestors of modern birds. These adaptations would have provided Temporalis with an enhanced respiratory system and improved thermal regulation, suggesting a level of physiological sophistication far beyond its contemporaries. How had such advanced features appeared so early in evolutionary history? The reconstruction of the creature's sensory capabilities painted an even more impressive picture. Three-dimensional models of its inner ear structure indicated an exceptional sense of balance and spatial awareness, while analysis of its olfactory bulbs suggested a sense of smell rivaling that of modern wolves. These advanced sensory adaptations, combined with its enhanced visual capabilities, would have made Temporalis an incredibly efficient hunter, able to track and pursue prey with unprecedented precision. Biomechanical studies of the creature's leg structure revealed another revolutionary finding. The combination of robust thigh bones and specialized ankle joints suggested that Temporalis could achieve bursts of speed approaching 50 miles per hour while maintaining extraordinary maneuverability. This level of athletic performance would have made it virtually unstoppable in its environment, able to outmaneuver and overtake any prey species of its time. The discovery of partially preserved skin impressions added another layer of complexity to the mystery. The impressions showed evidence of sophisticated scale patterns and possible thermal regulation structures, suggesting that Temporalis might have possessed advanced temperature control mechanisms previously thought to have evolved much later. These findings raised new questions about the evolution of dinosaur physiology and the capability for rapid evolutionary advancement. Evidence of social behavior emerged from the study of multiple specimens found in close proximity. Tooth marks on preserved bones suggested coordinated hunting strategies, while variations in skull size indicated possible sexual dimorphism. Could Temporalis have possessed advanced social structures and hunting strategies tens of millions of years before such behaviors were thought to have evolved? The implications for our understanding of dinosaur behavior were profound. The more researchers learned about Temporalis, the more questions emerged about its place in evolutionary history. How had such an advanced predator evolved so early? What selective pressures had driven the development of its sophisticated features? And perhaps most intriguingly, what had caused this apparently successful evolutionary experiment to end, leaving no direct descendants? These questions continued to challenge our understanding of evolutionary processes and the capabilities of ancient life. What other evolutionary marvels might remain undiscovered in the fossil record? How many other creatures might have developed advanced features far earlier than current models suggest? The study of Temporalis paradoxus was forcing paleontologists to reconsider fundamental aspects of evolutionary theory and the potential for rapid evolutionary innovation in prehistoric times. The discovery and analysis of Temporalis paradoxus has fundamentally transformed our understanding of dinosaur evolution and the capabilities of ancient life. 5 years after its initial discovery, the implications continue to ripple through the scientific community, challenging established theories and opening new avenues of research. The impact extends far beyond paleontology, influencing fields ranging from evolutionary biology to comparative physiology, and forcing scientists to reconsider basic assumptions about the pace and pattern of evolutionary change. One of the most significant implications has been the recognition that complex evolutionary innovations can appear much earlier than previously thought possible. The presence of advanced features in a Jurassic predator has led to a fundamental reassessment of evolutionary timelines. Research teams worldwide have begun re-examining existing fossil collections, searching for other examples of early evolutionary innovation that might have been overlooked or misinterpreted. This renewed scrutiny has already led to several promising discoveries, suggesting that Temporalis may not have been unique in its early development of advanced features. The impact on evolutionary theory has been equally profound. Traditional models of gradual evolutionary change have been challenged by evidence that sophisticated adaptations can appear relatively rapidly under the right conditions. Scientists are now developing new theoretical frameworks to explain how complex features might evolve more quickly than previously thought possible. These models incorporate factors such as environmental pressure, genetic plasticity, and the potential for rapid evolutionary response to changing conditions. Perhaps most intriguingly, the discovery has forced a re-evaluation of the fossil record's completeness. If such an advanced predator could exist in the Jurassic period, what other extraordinary creatures might have lived without leaving traces in the fossil record? Estimates suggest that less than 1% of all species that ever lived have been preserved as fossils. The existence of Temporalis raises the possibility that many other advanced forms might have evolved and disappeared without leaving evidence of their existence. The study of Temporalis has also led to technological innovations in paleontological research. New scanning techniques developed to analyze its unique features have now become standard tools in the field. Advanced computer modeling programs created to understand its biomechanics are being applied to other fossil specimens, revealing previously unrecognized capabilities in other prehistoric creatures. These technological advances have opened new possibilities for understanding ancient life. The mystery of Temporalis's extinction has sparked intense debate about the vulnerability of evolutionary innovations. Despite its advanced features and apparent success as a predator, the lineage seems to have disappeared without leaving descendants. This raises important questions about the stability of evolutionary innovations and the factors that determine their long-term success or failure. What conditions might cause an apparently successful evolutionary experiment to end? The answers could have implications for our understanding of modern biodiversity and conservation. The discovery continues to influence public understanding of prehistoric life. The realization that sophisticated predators existed much earlier than previously thought has captured public imagination and sparked renewed interest in paleontology. Museums worldwide have updated their exhibits to reflect this new understanding of dinosaur evolution, while educational programs have been revised to incorporate the possibility of early evolutionary innovations. Looking forward, the legacy of Temporalis Paradoxus extends beyond its immediate scientific impact. It serves as a reminder that our understanding of Earth's history is far from complete. Each new discovery has the potential to revolutionize our understanding of ancient life and the processes that shaped it. What other extraordinary creatures might still lie undiscovered in the rock layers of our planet? How many other assumptions about prehistoric life might need to be revised in light of future discoveries? The final message of Temporalis is perhaps the most important. The history of life on Earth is far more complex and dynamic than we previously imagined. As we continue to uncover new evidence and develop new ways of studying ancient life, we must remain open to the possibility that evolution can produce extraordinary innovations at any time. What other evolutionary marvels might be waiting to be discovered? How many other chapters in the story of life on Earth remain to be written? The search continues, driven by the knowledge that each new discovery has the potential to revolutionize our understanding of life's history. As we look to the future of paleontological research, one thing becomes clear. The study of prehistoric life will continue to surprise and challenge us, forcing us to reconsider our assumptions and expand our understanding of what is possible in the endless dance of evolution.